Hi there. Good morning. I want to share with you here a work through of the exam that was given as our exam FAR in Chem 130 in fall of 2019. This would be a good review for the upcoming exam in Chem 130. So I have here this exam. I've made two copies of it and labeled one of them as the key. It's in your OneNote notebook. I'm going to get my periodic table handy because definitely I'm going to need it to work on this. And so let's do some of these problems. So in the first question, we're asked to get the mass percent of phosphorus in phosphine, and what we're doing here is getting the mass percent from the formula. What we're going to do is we're going to assume that there's 1 mole of the phosphine, which means that we're going to have the molar mass of phosphine. We'll have that much in grams. So if we look at the periodic table, and I like to write the formula this way when I'm setting this up, so pH3 going down like that. If I look at phosphorus atomic weight is about 31. It's 30.97. We'll call it 31. And there's one phosphorus. You see the invisible one at the bottom of the phosphorus there. If you look at hydrogen, hydrogen's atomic weight is just about 1. A little more, but not very much more. And we've got 3 of them. So that's 31 for phosphorus and 3 for hydrogen. That's a grand total of 34. That is the molar mass of phosphine. It's 34 grams per mole. So if we're being asked to get the percent of phosphorus in phosphine, what we're going to do is figure out how much of that 34 grams of phosphine, how much of that came from phosphorus, and the answer is right there above. It's 31 grams of phosphorus. So percent is going to be equal to the 31 grams of phosphorus over the 34 grams of phosphine. And I always say that percent generally is part over whole times 100%. So our part here is the grams of phosphorus, and our whole is the grams of phosphine. And let me clarify my 34 there. It looks kind of like 39. 34 grams of phosphine. So the bottom number is the molar mass, and the top number is what part of that molar mass came from that element. So again, always good opportunity for you to check your calculation skills and make sure that you're getting the same answer I do. I get 94.2% for this answer. So I'll be looking for something close to that. Now, if we'd been asking for the percent hydrogen, so let's change this. This is percent phosphorus. Percent phosphorus. Percent hydrogen would have been 3 over 34 times 100%. And I would bet that that's going to be 5.8%. And the reason I bet is that they've got to add up to be 100. And, oh, you know what? I see that I got my first answer wrong. I misread it. It's not 94.2, it's 91.2. And so this one actually came out to be 8.8, not 5.8. So kind of doing that, checking that, helped me see my mistake. And that was simply just a miscopying of an answer from my calculator to my test. So that mistake happens. All right, second problem here, basic mole to gram conversion. We're going to look at the periodic table, and we'll see that, you know, if we look at sodium, sodium is element number 11, and it has an atomic mass of something like 22.99. Chlorine is element number 17. Its atomic mass is something like 35.453. So again, those are what the boxes would look like on the periodic table for sodium and chlorine. I'm going to call that 23. 23, let's try that again. 22.99, whatever, is about 23. 35.453, I'm going to round off to 35.5. That's not a bad rounding job on that. So I've got 1 sodium and 1 chlorine, all right? So NaCl, 23 times 1, 35.5 times 1 is going to be 23 and 35.5. I know that all seems obvious. That's 58.5, and that is the molar mass. That's grams per mole of sodium chloride. So our question asks how many grams. So that's X grams are equal to 1.43 moles. That comes from that part of the problem, right? So you see how we set this up with an equal sign, and Rn basically is our equals there. So we're going to want to put a conversion factor here, and that conversion factor is going to have moles on the bottom and grams on the top, because we're trying to go from grams to moles, and that conversion factor is our molar mass, right? So we'll say 1 mole is 58.5 grams, and again that's specific to sodium chloride. So 1.43 times 58.5, I don't have to do the divide by 1 because that's going to be the same answer. That comes out to 83.66. Maybe 83.7 grams would be the appropriate answer there. That is our answer. And you can see that, remember, this line means divide. Moles divided by moles cancels out. We have units of grams left. All right, so that's fairly simple gram to a mole to gram conversion. A gram to mole conversion would be easy to imagine as well. All right, question 3, we're given a balanced equation, and we're asked to figure out how many moles of water can be formed from our 82 moles of ammonia. So our question is how many moles of water, so X moles H2O, are equal to 82 moles of ammonia in H3. And then if I look at my equation, I can see that I have a 4 in front of ammonia and a 6 in front of water when it's balanced. That gives me a conversion factor, and that is that every time 4 moles of ammonia react, 6 moles of water form. And if I think about my units, I've got moles of ammonia up top here. I'm going to want to put that right down there. So moles of ammonia go here. And note that we're thinking not only about the unit, moles, we're also thinking about the substance, ammonia. So, and then moles of water will be on the top, and my numbers will come from that. So 6 moles from right there, and this 4 moles here will show up right there, 4 moles of ammonia. So moles of ammonia cancels out, and my math is 82.0 times 6 divided by 4, so 82 times 6 divided by 4, I get 123 moles of water as my answer for that question. And of course, that balanced chemical reaction equation actually gives us about a dozen different mole-to-mole conversion factors. Next question asks us to put that together with the gram to mole conversion factors as well. So we've got a balanced chemical reaction equation here for copper reacting with sulfur. We're given that we formed 1.17 grams of the copper 1 sulfide. And so we're being asked what mass of actual copper should we have reacted. So the question is how many grams mass of copper, okay, that's that bit, is equal to 1.17 grams of Cu2S. So we've got 2 different substances, which means that we're going to have to go through moles to get from one to the other. First thing we have to do is convert our grams of copper sulfate into moles of copper sulfate, copper 1 sulfate I should say. So I've got to think about that, so I'll do it down here. Cu2S. S is 32 basically, and we got 1. Copper is one of those ones that is about a half. It's 63.5, and we got 2 of those. And 63.5 times 2 is 127, and 32 times 1 is 32. So I'm getting 159 grams are in 1 mole of copper sulfide. And, you know, I'm just careful enough. I'm going to check my mental math there. But yeah, 63.5 times 2 is 127 plus 32 is 159. So that number is correct. So at this point, we can say that we've canceled grams of copper sulfate out. Now we want to go from moles of copper sulfate. So that's going to go on the bottom here, copper 1 sulfate, sulfide, excuse me, copper 1 sulfide. And we're going to copper, because we're trying to get the grams of copper, so we're going to go to moles of copper. So we're going to go look at our equation. We see we have a 2 here in front of copper, so that 2 goes there. In terms of copper sulfide, we just have a 1. And at this point, I can cancel out moles of copper 1 sulfide because it's on the top and on the bottom of the division line there in the middle of the problem. So at this point, our units are moles of copper, and so what we need is we need a conversion factor that has moles of copper on the bottom and grams of copper on the top, and of course that's the molar mass of copper, which is going to be the atomic weight of copper, which, as we said, is 63.5 if you look on the periodic table, and that would cancel out moles of copper for us. So, math-wise, I've got 1.17 times 2 times 63.5 divided by 159. I can leave all those ones out because they're not going to change anything. So let's plug it in the calculator. 1.17 times 2 and times 63.5. And then if I divide that by 159, I get 0.935. So 0.935 grams of copper would be my predicted amount that I had to start with to produce the 1.17 grams of copper 1 sulfide. Okay, so we have here a reaction of magnesium reacting with oxygen to form magnesium oxide. You'll probably get an opportunity to do this in Chem 111 lab when you take it. It's a pretty dramatic thing. You've probably seen this happen if you've seen fireworks. Magnesium frequently is a component in fireworks, and it burns an oxygen with a brilliant white light. It's almost dangerous to look at it if you're very close to it, and produces this magnesium oxide. What we're told a little sneakily here about how much oxygen reacted. So when we say the mass of the solid increased, right? So our solid is magnesium and then it turns into magnesium oxide. If we say the mass of the solid increases by 0.335 grams, well, what made it increase? It wasn't because more magnesium was added to it, right? The magnesium was already there. The thing that was added was oxygen. So what that tells us is that we had 0.335 grams of O2 that reacted. And so we're going to use that to get the mass of magnesium metal. So how many grams of magnesium would react with 0.335 grams of oxygen? All right, so we're going to first off convert oxygen to moles. So moles of oxygen over grams of oxygen. It's kind of handy to remember that anytime you have grams and moles in a conversion factor like this, you're always going to have 1 mole. It's always going to be 1 mole. If you look at oxygen, oxygen has an atomic weight of 16. We've got 2 of them, so that's going to be 32. And we don't have to belabor that, I don't think. And then if we look at our reaction equation, what we see is that for every 1 mole of oxygen that reacts, and I'm looking at that invisible 1 there in front of the O2, 2 moles of magnesium will react. And that's that 2 right there, is where that 2 came from. So that lets me cancel out moles of oxygen. And then if I go to the periodic table and I look for the atomic weight of magnesium, I find magnesium is one that is 24.3, and again that's kind of in the middle, so I'm probably not going to round it off. I'll just call it 24.3. Now I can cancel out moles of magnesium, and I calculate my answer. So it's going to be 0.335 divided by 32, then that times 2, and then that times 24.3. Again, I encourage you to work these and make sure you're getting the same answer I do, because you can make calculator errors on these, and you want to be practiced with your calculator before you take your exam. This comes out to me to be 0.509, 0.509 grams of magnesium is how much should have reacted. Okay, moving on. We're next asked about calcium chloride dissolving in water, and we're asked how many total ions, or moles of ions rather, are in solution. So the first thing you have to recognize here, there's a mole problem. We're going to figure out how many moles of calcium chloride we have, but then we have to think about how does calcium chloride dissolve in water. So if I put calcium chloride in water, so I'm going to write that as CaCl2 solid arrow with water underneath it, I'm going to get calcium 2+ ions, and I'm going to get 2 chloride ions. So every 1 mole of calcium chloride is going to give me 3 ions, or 3 moles of ions, where that 3 is the invisible one here plus the 2 there. Those give me that 3. So I'm going to use that conversion factor in a bit. And again, this question does kind of test whether you remember what ions form in solution. In previous chapters we talked about monoatomic and polyatomic ions and naming things and all that. And that skill is coming back in this question. So to get the moles of calcium chloride, we have to go from grams to moles. So I'm going to say how many moles of ions are equal to 5.0 grams of calcium chloride. And calcium is, put over here, calcium is 40. We've only got one of them. We'll call it 40. We got 2 chlorines. Chlorine's 35.5 times 2. That's 71. That is 111, I think. And that is our molar mass of calcium chloride. Again, in chemistry, frequently the math isn't terribly hard. It's just that it's all different for each substance, and you've got to figure out what the numbers are that apply, like the molar mass in this case. The good news is we give you the periodic table on the wall, so you can do that. And once you figure out how to do that, you're usually in pretty good shape. All right, so we've multiplied our 5 grams of calcium chloride by 1 mole over 111 grams. Grams of calcium chloride will cancel out. We'll have moles of calcium chloride at that point. And then we figured out from our dissolution equation up at the top that 3 moles of ions, specifically 1 calcium ion and 2 chloride ions, dissolve every time 1 mole of calcium chloride dissolves. And that lets us cancel out moles of calcium chloride. So we're going to have 5 divided by 111. And then multiply that by 3, and when I do that, I get 0.135. I guess I should only claim 2 here since it's 5.0. So 0.14 moles of ions is what I get as my final answer for that. Moving on to question 7 here, we've got nitrogen monoxide reacting with oxygen, and we've got a balanced equation, and we're given now the amount of nitrogen monoxide and the amount of oxygen that are reacting. So this is what we call a limiting reactant problem, where we don't know if oxygen or nitrogen, which one of those is the limiting reactant. One of them is going to run out first, and so to get the correct answer, we have to figure that out. Now, the method that I suggest doing is just go ahead and calculate what we're being asked to calculate twice. The first time we'll say how many moles of NO2 will we get if we have 12 moles of NO reacting. And that we can get from the equation that we're going to have 2 moles of NO2 if 2 moles of NO react. And again, those 2's are coming from here and here. Moles of NO cancel out. 12 times 2 divided by 2. I think I can do that in my head. That's 12 moles of NO2. So that's one possible theoretical yield for this in moles. Is it the right one? Let's see. How many moles of NO2 can we get if it's dependent on the number of moles of oxygen, right? So what we see here is that 2 moles of NO2 form every time 1 mole of oxygen reacts. Moles of oxygen cancels out. 10 times 2 divided by 1, that's 20 moles of NO2. And so what this tells me is that this, the lower one, is the correct yield, or theoretical yield. So I'd circle that as my answer. And that identifies the limiting reactant, and that is going to be NO in this case, since that calculation was based on NO. That tells us NO is the limiting reactant. There are some books that will tell you to figure out the limiting reactant, then figure out the theoretical yield. I'd say just go ahead and calculate the theoretical yields and using both reactants, doing it separately, and see which one gives you the lowest, and that identifies it, and then you're already done with your theoretical yield calculation as well. All right, so question 8 takes us one level further with this. We've got iron and chlorine, and we're given grams now in this compound, in this reaction, grams of each. So it's another limiting reactant theoretical yield. It has the added complication that we've got to figure out the gram to mole and mole to gram conversions as well. So let's jot some molar masses down. I'm just going to jot them up here to get them out of the way. So iron is 55.6. Chlorine is 71. And FeCl3, I'm going to have 55.6 plus 3 times 35.5. That's going to be 162.1 for this guy. So those are our molar masses, just to have them handy. The molar ratios are given by those coefficients. And so what we can do is we're going to do our two calculations. So the first one is how many grams of FeCl3 are equal to 35 grams of iron. And then after we do that, we'll do how many grams of FeCl3 are equal to 35 grams of chlorine. Okay, so the first thing we're going to do is convert, we'll work on the top one, we'll convert grams of iron to moles. 1 mole of iron is 55.6 grams of iron. That lets grams of iron get canceled out. And then from the equation, we see that 2 moles of FeCl3 are produced every time 2 moles of Fe react. And then finally, 1 mole of FeCl3 is 162.1 grams of FeCl3. That's a 3, not a 2. All right, so I can cancel out moles of iron here. I can cancel out moles of FeCl3 there. And so the math is 35 times 2 divided by 2. Well, I can cancel those out as well. 35 times 162.1 divided by 55.6. And again, checking my math here carefully that I do it right. 35 times 162.1 divided by 55.6, I get 102 grams of my FeCl3 if the iron is the limiting reactant. Now, when I look at chlorine, I'm going to go from grams of chlorine to a mole of chlorine, and that's 71 grams of chlorine on the bottom. And then my mole to mole, I'm going to have 2 moles of FeCl3 on the top again. But on the bottom, I'll have 3 moles of Cl2. And that will cancel out moles of Cl2. And then the end one's going to look the same. It's going to be 162.1 grams of FeCl3 over 1 mole FeCl3. And that will let that cancel out as well. And that's one of the reasons I say that this is just easy to go ahead and do this, is that half of those, the calculations, like starting with the top of the second conversion factor to the end of the calculation, is the same stuff. So it's not like you have to rethink it a lot. All right, so I've got 35 times 2, this type, times 2, times 162.1. Divided by, and I'm going to put the bottom in a parentheses, 71 times 3. What do you think? Do you think this is going to be bigger or smaller? I think we're dividing by a bigger number on the first conversion factor. We're dividing by a bigger number on the second conversion factor. I think it's going to be smaller. I think chlorine will be our limiting reactant, and indeed it is. It's 53.3 grams of FeCl3. So that gets us our yield, and the limiting reactant is chlorine. So we've identified that as well. And again, that's the two things we're asked in the problem, how much FeCl3 should form and which is the limiting reactant. So we box both of those in. All right, next question. I've written over it a little bit, but I think we can still sort it out. We're told that the theoretical yield for a reaction is 54.9 grams and that the 51.3 grams of product are actually obtained. We're asked to calculate the percent yield. So the percent yield is the actual yield divided by the theoretical yield times 100%. So we're told in the problem that the theoretical yield was 54.9 grams. And the actual yield was 51.3 grams of product actually obtained. That's actual yield, right? So fairly simple here, 51.3 divided by 54.9. That, then multiplying by 100, I get 93.4% yield is my answer to that question. All right, so next one, we're going to put that together with a stoichiometry problem. We've got aluminum reacting with sulfuric acid, making aluminum sulfate and hydrogen gas. And what we are given is an actual yield here of aluminum sulfate based on 10 grams of aluminum. We have excess sulfuric acid, so this tells us that Al is the limiting reactant. Right, so we don't have to worry about sulfuric acid. So we know the actual yield. We need the theoretical yield, and the theoretical yield is how many grams of Al2SO4, and that SO4 is taken 3 times. How many grams of that will we get if we have 10 grams of aluminum? And so aluminum is 27. Molar mass of aluminum is 27. Aluminum sulfate is a fairly, oops, where'd you go? One note crashed on me there or what? Let me bring it back over here on the right screen. All right. Get that back. Sorry about that. All right. I probably just bumped something with my hand there. Aluminum sulfate is a pretty advanced molar mass calculation there. So what we're going to do is we're going to think about, that 3's got to go through both of these. So I've got Al2S3O12. Aluminum's 27 times 2, that's 54. Sulfur is basically 32 times 3, that's 96. Oxygen is 16 times 12. Well, oxygen, 2 times 16 is 32. 10 16s is 160. So I'm getting 192 for that one. So just to be on the safe side, I'm going to do it in the calculator the long way. I'm going to say 27, parentheses 27 times 2, close paren, plus parentheses 32 times 3, close paren, plus parentheses 16 times 12, close paren. All right, so what I got here is I'm going to add this up. I'll do the hit enter in a second. So 6 plus 4 is 10, 2, carry my 1. 1 and 9 is 10, 10 and 5 is 15, 15 and 9 is 24, 4, carry my 2, 342. Let's see if the calculator agrees, and the calculator agrees. Excellent. So we now know this guy is 342 grams per mole for that one. So we're going to say 10 grams of aluminum, 1 mole of aluminum is 27 grams of aluminum. We've got grams of aluminum there. Then we're going to take moles of aluminum and moles of the aluminum sulfate. And the equation tells us that if we form 1 mole of aluminum sulfate, 2 moles of aluminum must have reacted. And then we're going to use that big number we just figured out, that 1 mole of our aluminum sulfate is 342 grams of that aluminum sulfate. Okay, and so grams of aluminum cancels out, moles of aluminum cancels out, moles of aluminum sulfate cancels out. We'll have grams of aluminum sulfate. So here we go. 10 times 342 divided by parentheses 27 times 2, and that comes out to be 63.3. So 63.3 grams Al2SO4 taken 3 times. That is our theoretical yield. Our actual yield we're given was 54.2. Our percent yield, again looking at the previous problem, we put the actual yield, 54.2, on top of our theoretical yield, 63.3, multiplied by 100%, and 54.2 divided by 63.3, that comes out to be an 85.6% theoretical yield. And that's what we're asked, so we put a box around that guy. So anyway, so that concludes this this exam. Obviously, pretty short, very problem-oriented exam. I hope that reviewing that helps you be prepared for what's coming and for the exam in class.